Hi, in this video we will talk about the base plausible and split lemma. Okay, so first let's see what is base plausible or base plausibility. So intuitively, base plausibility, it means that the expectation of the posteriors is just the prior. Okay, so that's a very straightforward and brief introduction for that. So it means that the expectation of the posterior belief is just the prior. Okay, and later shortly we'll discuss the rigorous definition of that. Okay, so when we have the base plausibility, so we can introduce something called split lemma, which is used later for us to establish our understanding for the Bayesian persuasion problem. Okay, so talking about split lemma, okay, or splitting lemma. So essentially, it's saying that a distribution over the posterior belief, this distribution, it can be induced by a signal or by an information structure, if and only if this distribution of the posterior belief, this distribution is base plausible. Okay, so we can write something more straightforward here in the beginning. So let's say a tau, okay, which is a distribution over the posterior. It can be induced. So whenever we see induced, this means that we use the Bayes theory, right? So this can be induced by a signal or an information structure, the same thing. If and only if this tau is Bayes plausible, okay? So it means that this tau, with this tau, then the expectation of the posteriors is prior, okay? Okay, so now we can formally define or formally demonstrate this splitting lemma, okay? So formally, so given a prior, so given this prior mu naught, okay, so distribution of the posteriors, okay, tau, okay, which is the delta omega, okay, so this tau, okay, it is induced by some signal if and only if this tau is Bayes plausible, okay. So this definition is more rigorous to be used later, okay. So let's formally prove that. So we have two directions. So first, let's show the direction from the former to the latter. Okay. So suppose that this tau is induced by some pi. Okay. So that's our assumption, and that's what was given to us, right, to prove the latter Bayes plausibility. So for all omega, the summation, okay, or the that where we're trying to show the Bayes plausibility, right? So here we're trying to to find the expectation of the posterior. So the posterior times the probability of posterior and sum over all the posteriors. Okay, so and then we remove all the parts with zero probabilities. Then this becomes the ones with only positive supports, positive probabilities in the support. So this is mu s, given those s with positive probabilities, and tau mu s, right? Okay, then what we need to do next is just to plug in the those two terms, right? Okay, so for the first term is that we just use the base rule, right? So which is pi s omega mu naught omega, and over all the probabilities, right? Having this signal s omega pi s omega prime mu naught omega prime. Okay, so that's the first part. So the second part becomes this probability of the mu s is just the denominator, right? So it's just this thing. So omega prime pi s given omega prime mu naught omega prime. So this and that, they cancel each other, right? And the only thing left is just the remaining parts. So it becomes this. Okay, and further, this thing sums to 1, right? For all the possible signal realizations. So finally, this becomes the prior. Okay, and then we have proved this direction. Okay. All right. How about the opposite direction? Okay. Now we need to construct some signal, right? Which satisfies the base plausibility, and then we construct that signal, and to verify that this signal is actually a valid signal, right? So now let's do that. So first, let's define something. So we let mu s for all s. This is the support of the tau. Okay, so it means that it has the positive probabilities of having those points, right? Otherwise, they all have the zero probabilities, right, outside of this support. So we define, or more rigorously, we are actually construct a signal, okay, pi, such that, so this pi that we are going to construct looks something like this, okay? So mu times its probability over the prior, okay? And later we'll see that this denominator, the prior in the denominator here, is useful for us to make this pi as a valid posterior, as a valid signal, okay? It's just for the normalization. So then we apply the base plausibility, right? So by the base plausibility, okay, for all the s and omega. So the base plausibility means that the expectation of the posterior is prior, right? Okay, so what we're going to do here, two things. The first is that we need to verify the probability of this tau is 1, right? The sum of that is 1. The second thing is that this pi can actually induce a tau, right, over the mu s, right? So this is what we are trying to verify here is it is essentially we're actually verifying the Bayes rule, right? Okay, verifying the Bayes rule. Okay, so now let's first start with the first part. So to show that the summation of the probabilities, to make this a valid distribution first, right? So, okay, now we simply look at this pi. Okay, what it is, it's just that, right? So we copy and paste this. So mu s omega tau. So if we sum over the two sides together, okay, over all the s, and what we can see here is that actually, so here we use the Bayes plausibility and plug in here, and then this becomes 1, right? Mu naught over mu naught. So this is 1. And so that means that this pi is a valid distribution, right? Okay, now let's check the second thing. Okay, so that such that the pi actually it can induce the tau over the mu s, right? So so the second thing here, pi is omega mu naught. As mentioned, we're trying to check that if the Bayes rule it works here, right? So it means that we're trying to show that the posterior is induced from the prior using the Bayes rule and with this signal pi, right? And this mu naught. So that's what we're doing here. So the numerator is the pi times mu naught, and and the denominator is the summation of all the possibilities sending s signal realization s. So pi s omega prime mu naught omega prime. Okay, so and we're trying to verify if this equals to mu s, right? The posterior. If it is true, then we have proved, right? Proved that. Okay, so now let's forget about those first and calculate the left hand side here. So and it's pretty straightforward. We just need to plug in all those terms for the pi's, okay? Because we have already define or construct those pi's. So we just plug in the numerator is mu s omega tau mu s over mu naught omega. Okay. Remember that we put something here, right, when we construct the pi. That's for us to cancel with this mu naught. Okay. So that's pretty interesting. And over summation omega prime mu s omega prime tau mu s mu naught omega prime mu naught omega prime. Okay, so those mu naught, those are cancelled. Okay, so the thing left is just mu times tau over the summation of mu times tau, right? Okay, and again, this thing is 1, right? Over all the possible possible states, right? So this finally becomes mu s. Okay, so then from here, we have show the other direction, the inverse direction, right? By constructing some signal to verify that this signal is actually, if it is based plausible, then we verify this is a valid probability distribution, and this positive belief is induced from the prior given some signal. Okay, so that's the splitting lemma, and that we'll use that for the proof in the next episodes for the Bayesian persuasion problem. Okay, and this Bayes plausible idea of this Bayes plausibility is also very important for us to know. Okay, all right, that's it.